So this next example that we'll be looking at here is a set of bolt cutters. So in it we've got a worker who is able to apply a 300 Newton force to each side of the handle. And then we want to figure out how much force that translates into cutting at the bolt. So we're trying to find out what the force is here on the bolt. We're going to call that F bolt. So just looking at the bolt cutters themselves, we just do a free body diagram of the bolt cutters themselves, we're not getting much. We're getting the 300 Newton forces on either side, and those are balanced, and then nothing happens. So we're going to have to break this machine up into its components and then figure out what happens there. So I'm going to take the top cutting piece here, so this thing here, and do a free body diagram of that. So got that. We've got the three forces that are acting on it. The force of the bolts. So if we're pushing down onto the bolts to try to cut it, the bolt will be pushing back as well. Good old Newton's third law. We've got the force in this link here, this FAD. And that link there, that's a two force member there, right? So we know the directionality of that. We know that it doesn't have any, if we define our axes as x and y like this, which I forgot to when I was writing it out, but anyways, we know that it's only going to have a force in the y direction. It's not going to have any forces in the x direction. And then we've got the reaction here at B. So at B, we're going to have a reaction in the y direction, and we could have a reaction in the x direction, but when we sum the forces in the x direction, 0 is equal to bx, so there is no bx there. So three forces, all in the y direction, acting on this thing. So we want to get some useful information out of this. Let's go ahead and take a moment. So I'm going to take a moment about A. So it's about this point here, and that's going to be equal to 0. So the moment caused by the bolt is going to be a clockwise or a negative moment. It's going to tend towards clockwise rotation. And it's the force of the bolt times the 24 millimeters between the link and where the bolt is placed. And then we've got the reaction force at B. So it we default to our assumption that it's pointed upwards. So that times the 96 millimeters. Again, if it is pointed upwards, that would be a positive movement. Positive moment. So the magnitude of By, we can relatively easily solve for. That's just going to be the force in the bolt times the 24 millimeters divided by 96 millimeters. So 1/4 of the force in the bolt is the By reaction there. So that's on this one. So on this one, on this free body diagram, it is pushing upwards. If we go to the handle, on the other hand, it's a different situation because it's an equal and opposite reaction. So on the handle, the reaction from B is pushing downwards, but it is still, the magnitude is the same, force of the bolt divided by 4, and then we got these other two forces. So we got the load, the squeezing force applied, and we got our reaction here at this pin C. So again, relatively easily we can toss out Cx there because the sum of the forces in the x direction is 0. Cx is the only thing that would be acting in the x direction, so it is 0 as well. No Cx. We do have the Cy, however. If we want to figure out kind of the magnitude of our force in the bolt, now we're going to need to find out what Cy is. So we can just take a moment about B. So taking a moment about this point, these are all the remaining forces are acting in only the y direction, so we're only worried about the x component of its displacement. So taking a moment about here, we've got the 300 newtons that we're applying, and that'll be a negative moment because that you know, from here that's a clockwise rotation that would be applied. And we also have the moment that would be caused by the 300 newtons times the distance from B to where the force is applied, so that's 460 millimeters. And then we've got the counteracting moment that would be applied by Cy. So again, that'll be a positive moment because pushing up from here would cause positive rotation, counterclockwise rotation, when taken about this point. So the magnitude of that will be Cy times the 12 millimeters. So we just need to go ahead and solve for what Cy is. So again, moving this over to the other side of the equation, multiplying it out, and then dividing by 12 millimeters gives us a Cy of 11.5 kilonewtons. And then we just need to take the sum of the forces in the y direction. So we have the negative F bolt over 4 plus the 11.5 kilonewtons minus 300 newtons. We can move the F bolt over 4 to the other side of the equation by adding it and then multiply by 4 to give us F bolt is equal to 4 times 11.5 kilonewtons minus 300 newtons, which gives us a total F bolt of 44.8 kilonewtons. And that's the joys of mechanical advantage. We do not need to squeeze very hard in order to generate quite a lot of force. That is why we are able to use bolt cutters to cut through bolts when, whereas if you were just trying to take those blades and press them together with your hands, ain't no way in hell that's ever going to happen. So yeah, that's a good old mechanical advantage. That's the point of machines, and that's it for now.